Okay. One example is remain from week 12. We want to extract the equation of motion for this system using Lagrange equation. And for this purpose, we need to consider a generalized coordinate system. In this problem, according to the problem description, we need to consider the x1, x2, and x3 as a generalized coordinate system. As you can see, x1 is the deflection of this point, the end point of this spring, the stiffness K. x2 is the displacement of this mass 5m, and x3 is the deflection of this point, which is the end point of this spring K, or the right end of the rod. So here we can write the kinetic energy and potential energy for this system. For this purpose, if you write the kinetic energy, we will have a kinetic energy for this mass 5m. It's clearly that kinetic energy is half m v squared, which the m, the mass in this case, is 5 times by m, and v is the velocity of this mass, which is x2 dot, because the displacement is x2. So the velocity is x2 dot, the squared is the kinetic energy. So this is the kinetic energy for this mass 5m. But we have, in addition to this mass, we have another mass 2m, which is this rod, and this is a rigid body. And this rigid body has a general motion. It means that at the same time it can rotate, and it will have translational motion. So the kinetic energy for this rod can be written as half times by mass, which is 2m, 2 times by m, times by the velocity of the mass center. The mass center of this rod is point G, so it will be Vg squared. And also, this is the kinetic energy due to the translational motion, or due to the velocity of the mass center. And also we have one kinetic energy due to the rotational, which is half times by JO, or the mass moment of inertia about the mass center, or JG, times by theta dot squared, which theta is the angular displacement of the rod. Here, this is theta with respect to the mass center. So this is the kinetic energy, but according to the problem description, we need to define Vg and theta dot as a function of x1, x2, and x3. So for this purpose, we can write a relation between theta and Vg. As you can see, point G is located at the center of this rod, and x1 and x3 are two end points for this rod. I mean, we can write the velocity of G as an average of the velocity of point x1 and x3. And also from the geometry, we can write a relation between theta and x1 and x3. So by using this geometry relation, we can write theta dot and Vg as a function of x1, x2, and x3. And the kinetic energy for this particle 5m is a function of x2, so it doesn't need any change. And also for the potential energy, if you look at to this system, again, we have two masses, 5m and 2m. Both of them will create some initial deflection in the system, so their gravitational potential energy will not appear in the equation. Only we consider the potential energy due to this spring, which is half k times by x1 squared. we have the potential energy due to this spring, which is again half k times by x3 squared. And also we have one spring here with stiffness k, but 2 edge of this spring are movable. So this spring will have a potential energy, and this potential energy is equal to half k times by the displacement squared, which the displacement is the displacement of point A minus the displacement of mass 5m, which is x sub 2, or x sub 2 minus xa, no different, squared. This is the potential energy in this spring. And now we need to define xa as a function of x1 and x3, because we need to extract the potential energy in terms of x1, x2, and x3, not xa. So again, from the geometry, we can extract the relation between xa, x1, and x3. And also because we need the xa to obtain the work done by this damper, because you know that the work done by this damper is again c times by xa dot minus x2 dot. This is the force in the spring multiplied by its displacement, which is again xa minus x2, and we need to use this spring. Again, we should substitute for xa and xa dot as a function of x1 and x3. So by using this geometry relation, we can extract the kinetic energy and potential energy as a function of x1, x2, and x3, and then we can substitute into the Lagrange equation. So the first step, we obtain the kinetic energy for this system. As you can see, it consists of these two terms, which are due to the rod, the rigid bar, half jo theta dot squared, which jo is the mass moment of inertia for this bar about the mass center. From this equation, you can obtain jo. And this is half times by the mass, which is 2m, times by the velocity of the mass center squared, which is xg dot squared. And finally, this term, which is the kinetic energy due to the mass 5m. So from the geometry, as I told you, xg, or the displacement of the center for this bar, is equal to the average of the displacement of x1 and x3. So this is the relation between xg, x1, and x3. And also for theta, we can write that theta is equal to the difference between x3 and x1 divided by the total length of this bar, which is 5L. Okay, so because theta is the rotation about the center, and this is defined as theta, so we can use this equation for the theta. So now we can substitute for theta dot, which is equal to x1 dot minus x3 dot divided by 5L. And for xg dot, again, we can substitute x1 dot plus x3 dot divided by 2. Clear? Any question? Any question? Is it clear? Okay. So the next step, we need to obtain the potential energy. And as I told you, for this purpose, we can write the displacement of point A as a function of x1 and x3. To find the expression for displacement xa, you can write the tangent theta relation in the small triangle, in this triangle. Let me show here this triangle, and also the big triangle, which is this triangle. You can write the tangent theta in these two triangles. In the first one, tangent theta is equal to this length, which is y, divided by this length, which is 2. And also in the big triangle, this length, which is x1 minus x3, because the total length is considered here, x1. So this length is equal to x1 minus x3 divided by this length, the total length of the bar, which is 5L. So we can substitute here and calculate and simplify. From this equation. You can obtain that y, which is equal to x1 minus in fact y is equal to x1 minus xa, or xa is equal to x1 minus y. So you can substitute here. From this equation you can obtain that y as a function of x1 and x3, y is equal to 2 divided by 5 multiplied by x1 minus x3. This is the relation for y, and now you can substitute here and obtain that xa is equal to x1 minus y, and from here you can substitute for y and simplify, and finally you will see that xa is equal to 3/5 times by x1 plus 2/5 times by x3. So this is the xa, and from here you can obtain xa dot as well. And now we can extract the relation for the potential energy. As you see, the potential energy is half k x1 squared due to this spring, half k x3 squared due to this spring, and of course here we have a plus, half times by k x2 minus xa squared for this spring. And finally, the work done by the external force. As I told you, this damper is considered as an external force, and the force is equal to C times by xa dot minus x2 dot, or x2 dot minus xa dot, and multiplied by its displacement, which is xa minus x2 or x2 minus xa. Here you should pay attention. If you considered here, the force in the damper is C times by x2 dot minus xa dot, then the displacement will be x2 minus xa. If you assume that xa dot minus x2 dot, again here you should consider that the displacement is xa minus x2. Okay, so the sign should be the same. For xa here you can see is negative, so for xa dot again it will be negative as well. And the work done by the damper is negative because the always this force, the direction of this force is opposite of the direction of the system. So we will have one negative sign. And also we have three external force which are applied at point here, at point which is measured x1, x2, and x3. So we will have three forces multiplied by the displacement to calculate the work done by these forces. So this is the W, and now we can calculate the work, the equation of motion by substituting into the Lagrange equation. And this is the Lagrange equation. You need to calculate the partial of t with respect to x I dot, which I is 1, 2, and 3. And also we need to calculate the partial of t with respect to xi. You need to calculate the partial of v with respect to xi from this equation, and finally the partial of w with respect to xi, which results in the qi. So from this equation you can calculate the partial of w with respect to x1, x2, and x3. Okay, so this is the last example from topic 12, and now continue with the topics for this week. Okay, for this week, we will discuss the Rayleigh's method for system with multi-degree of freedom and fundamental frequency of beams and shafts. Similar to the system with single degree of freedom, here in the system with multi-degree freedoms, sometimes it's not possible to obtain an analytical result or analytical solution to obtain the natural frequencies, which you know that the natural frequency and damping ratio are two important parameters that we need them to do the other analysis in our system. So similar to the SDOF systems, we can use the numerical methods or experimental methods to obtain the natural frequency in our system. Here in this topic, we will discuss the Rayleigh's method, which is one of the most popular methods in the numerical solutions is this method, and we use it to obtain the fundamental natural frequency. Of course, this is only an approximation in system with multi-degree of freedoms, and we use this approximation to find a minimum value for the fundamental natural frequency or for the first natural frequency in our system. As I told you, similar to the system with single degree of freedom system, for a system which is conservative, or there is no damping, or there is no component which causes to dissipating the energy, and we call it a conservative system, we can write the kinetic energy and potential energy as these two terms. Here, instead of the mass for the kinetic energy, we have the matrix of the mass, and instead of the K or the stiffness, we have the matrix of stiffness. And instead of the displacement X, we have the vector of displacement. As you can see, we have the vector X dot and the vector X. And by using this matrix form, we can obtain the kinetic energy and potential energy for a conservative system with multi-degree of freedom. Now we can consider the response as a harmonic motion similar to the SDOF systems, which in this definition, X is the amplitude of the response and omega is the frequency of your system. But here, because we deal with a system with multi-degree of freedom, in fact, this X is the vector of the mode shape. It's not exactly the same as the amplitude in the system with single degree of freedoms. And omega, which is the frequency of your system or the eigenvalue of your system. And here we want to obtain this omega by using a numerical method, which is called Rayleigh's method. So we don't need to extract the frequency equation similar to the previous method in analytical solutions. And here we want to only approximate the mode shape, this vector X, and then by using this vector X, we can obtain an approximation for the natural frequency. So for this purpose, we can consider, because the system is a conservative system, so similar to the SDOF systems, the maximum kinetic energy must be equal to the maximum potential energy. It means that when you substitute for X dot and X, the maximum value will happen in the amplitude. I mean, for example, for X, the maximum value of this term will happen when cosine omega t is 1. So the maximum value is the vector X. And for x dot, you know that x dot is equal to minus omega multiplied by vector x multiplied by sine omega t. Again, the maximum value for x dot will be happen when sine omega t is 1, because sine and cosine are in the interval of -1 and 1. So the maximum value for these two functions are value 1, and the maximum value for x dot is minus omega x. Okay, so here in this equation, when you want to calculate the maximum t or the maximum kinetic energy for x dot, we should substitute the maximum value, which is minus omega x multiplied by, again we have another x dot, so again it will be minus omega x, and then we will have half times by x transpose times by m times by x omega squared. This omega squared is due to, here we have 1 minus omega due to the x dot, and the other one due to the x dot transpose, so it will be omega squared. And for the potential energy, when you want to calculate the maximum value for the potential energy, again in this vector it must be the maximum value, which is vector x. So instead of x, we substitute vector uppercase x, so it will be half x transpose multiplied by k multiplied by x. So from here we can obtain that the frequency omega squared is equal to this term, and in this term we need only to obtain the vector for the mode shapes. You know that matrix K and matrix M can be calculated from the equations of motion. So for this type of problems, we need to use an approximation for the mode shape. And you will see we at the first we need to assume an initial value for the mode shape, and then we can substitute here and calculate the omega. And then if you want, you can modify your results by adjusting the mode shape and again substitute into this equation. Okay, for example, here we want to, using the Rayleigh's method, find the fundamental natural frequency of the torsional system. Here in this system, we want to assume that J1, or the mass moment of inertia for the first system, is J naught. J2, the mass moment of inertia for the second turbine, is 2J naught, and J3, the third mass moment of inertia, is 3 times by J naught. The equivalent stiffness KT1, KT2, and KT3 are equal to K3. So as I told you, we need to assume an initial mode shape. We assume that the mode shape is 1, 2, 3, and it can be according to your geometry and your system, you can guess this mode shape. So here we assume that 1, 2, and 3, it means the relation between the amplitude of the response theta 1, if we assume is equal to 1, the amplitude of the response theta 2 here for this one is times by 2, and for the last one, theta 3 is equal to 3 when we assume that theta 1 is equal to 1. So this is the assumption for the mode shape. Now the equation of motion can be extracted. You can obtain the equation of motion easily using any methods. I mean, you can use the Lagrange equation, or you can use the Newton's second law. If you write the Newton's second law, you can plot the free body diagram for each system. Here we have one mass moment of inertia. We have one force due to this spring KT2, and also we have one force due to this spring KT1. We have an external moment MT1. So you can write the force in this spring. Of course, the moment in the first spring KT1 is equal to KT1 times by theta 1, and the force in this spring is KT2 times by theta 1 minus theta 2. So you can extract the equation of motion for each mass, and you can obtain these equations, three equations with three unknowns, theta 1, theta 2, and theta 3. And also you can write it in matrix form. If you write it in matrix form and substitute from the problem description for J1, J2, J3, KT1, KT2, and KT3, you can extract these two matrices, and by using the initial assumption for the mode shape, which is this vector, and substituting into the equation, you can obtain the natural frequency as a function of KT and J naught. Of course, this is a simple example. I mean, by using the analytical method, you can extract the natural frequency for this system, and you can compare it with this system because you have the matrix M and K. So if you form the matrix K minus matrix M times by omega squared, if you find this matrix, and for example, if we call it matrix C, the determinant of this matrix must be equal to 0. And from here, you can obtain the characteristic equation and obtain omega 1, omega 2, and finally omega 3, which omega 1 in fact is this term, and you can compare it and you will see that and you can compare the accuracy of your numerical method and numerical results with this analytical value. Okay, so for this simple example, you can obtain the analytical solution, but sometimes it's not possible to obtain the analytical solution. Maybe we can have the nonlinear terms, nonlinear components, or due to the large displacement, or sometimes the equation of motion is very complicated, and we prefer to use the numerical methods. The last topic for this section is the fundamental frequency of beams and shafts. Here, again, we only consider a simple case. As you know, this shaft, in fact, is a continuous structure. I mean, in fact, when you deal with a shaft, and it's not a rigid shaft usually, this is a system with infinite degree of freedom, and it can have infinite natural frequency. So it's not a system with multi-degree of freedom, or it's not a discrete system. This is a continuous system. But as I explained in chapter 1, sometimes we can model these continuous systems as a discrete system and obtain the characteristic for this type of system. For the shafts, most of the time, we assume that this shaft is equivalent with a system of one shaft without any mass and several concentrated masses. These masses can be assumed, for example, with mass M1, M2, and M3, which in fact they are equivalent with the total mass of the initial shaft. And we can model this system as an equivalent discrete system like this. So in this section, in fact, we want to obtain the fundamental natural frequency for a system, for an equivalent system of a continuous shaft with several masses. For each mass, we assume that the deflection is equal to W. For example, for mass M1, the deflection is W1. For mass M2, the deflection is W2. And for mass M3, the deflection is W3. And it is clear that by increasing the number of these masses, we can achieve a better approximation for this continuous system. Because here, for example, we assume a system with 3 degrees of freedom. If you increase the number of the masses, in fact, you are increasing the degree of freedoms. So you can find a better approximation for your continuous system by using this discrete system. So by using the Rayleigh's method, again, we can extract the equation for the potential energy. The maximum potential energy is equal to half m1g times by w1, which is in fact the strain energy of the shaft. And we have half times by m2gw2 and so on according to the number of the masses. We have the the kinetic energy, which is equal to half mv squared, half times by m1, and v is equal to r omega. You know that when we have a rotational motion, for example, assume that this is a mass m which is rotating about this point O with angular velocity omega and the radius r. So the displacement, if we call it the displacement v, in fact is equal to r times by omega. So for each mass, when it has a deflection of omega w1, sorry, the w1 times by omega will be the velocity of this mass m. So v squared in fact is w1 times by omega squared. For mass m2 it will be w2 times by omega squared, and for m3 it's equal to w3 times by omega. Again, from the Rayleigh's method you can extract a relation for omega squared as a function of m1 and w1, and also g, which is the 9.8, and this is the gravitational acceleration. So by using this equation you can obtain the fundamental natural frequency for a shaft for a continuous system. But again, I should mention that this is only an approximation. We use two different approximations to extract this natural frequency. The first approximation was when we model the continuous system as a discrete system, and the second approximation is using the Rayleigh's method, because we are using the Rayleigh's method to obtain the natural frequency. So by using this method you can obtain the lowest value for the natural frequency in a continuous system without extracting a quotient of motion for a continuous system. Here you can see we deal with shaft. In this example, figure shows a steel stepped cantilever beam. The steps have square cross sections of size 16 inches squared and 4 inches squared, each with a length of 15 inch. Assuming the Young's modulus as E is equal to 30 mega psi, and the unit weight as gamma is equal to 0.283 pound per inch cubed for the material of the beam, determine the fundamental natural frequency of bending vibration of the beam using the Rayleigh's method. Assume the deflection of the beam as Yx. This is the deflection of the beam by using this equation, where C is a constant. So again, here, similar to the previous example that we assumed one approximation for the mode shapes, here we use this equation for the deflection in the beam. So by using this equation, we can obtain the omega squared. You know that W1, which is the deflection of point with mass m1. Here we have two different masses. One is the first part of the beam with the cross section 16 inches squared, and the second mass is this beam with the cross section 4 inches squared. But here, instead of using the summation of the mass times by W or times by the deflection, because this is a continuous system and we have the deflection for each point as a function of X, so we can substitute into the integral form of the equation. I mean, instead of the mass times by W1, we will have the mass per, or the density times by mass per volume, or density times by the deflection of each point as a function of x multiplied by the cross section. So here we can substitute for the numerator of the equation. We'll have, this is for the first part. You can see this gamma multiplied by a1 in fact is the m1, g is the g, and y times by dx, which is in fact the w1. For the second part of the beam, again we have gamma times by a2, which is the m2 in fact, the second mass, multiplied by y dx, which is w2. And in the denominator, instead of m1 w1 squared, we have gamma times by a1. Of course, we don't have g in this term. This is, I made a mistake here, typo error. Gamma times by a1, which is the m1, and y squared times by dx, which is w1 squared. And here again gamma times by a2, and again we have a typo error, this g must not be here. This is m2 multiplied by w squared times by dx, which is in fact w2 squared. This is the denominator by substituting for yx, because here you can see that yx is a function of x. You can substitute here and calculate this integral, and you can calculate the interval of the integrals. You can see the first term is from 0 to L over 2. For the second one is L over 2 to L, and L is equal to 100 inch. So you can substitute and calculate the omega and find an approximation for the first natural frequency of this beam by using the Rayleigh's method. Okay, so this is the numerical method that we can use for the system with multi-degree of freedom system. Of course, this is an approximation again for the first fundamental natural frequency in your system. Okay, any question from this part? No questions? Okay, thank you for your attention, and we can continue on Wednesday. Thank you.